Okay, great. So I uploaded some things as announcements for efficiencies, and I'll upload some more kind of problems that you can look at. There's not too many things you can do with efficiencies and stuff. Once we get into entropy calculations, some of the calculations may be a bit more involved, but as I said, if we keep in mind the things that I really, really emphasized last class, which is that entropy is a state function, and all you need are two equilibrium points to compute delta S. And to compute delta S, the way we have done it so far is to imagine or construct a reversible process between those two equilibrium state points that you're interested in, regardless of whether the actual process that you are looking at, which invariably will be irreversible, is irreversible. And so this is the beauty of state functions. Okay, again, if you, from the beginning of the course, if you've been wondering who the heck cares, this is why, particularly when we get into this very obtuse concept of entropy. Okay, so I'm going to open up the floor for any questions so far for clarification. If not, then I'm going to continue, and we're going to actually see how we can apply these concepts that I really emphasized last class today. So anybody wish to contribute or comment or anything like that? Okay. Well, then let's go on, and we can see where this leads us to. Okay, we'll continue, and believe me, I will clarify a lot of things as we go along. You just have to be patient. Okay, so from our discussion of the Carnot cycle, we came by analogy to a function. If you have your Carnot cycle, and if you were to just consider the U, the internal energy of the gas, the ideal gas in the system, you would see that delta U's sum up for each one of these stages. And we know that since U is a state function over the cycle, then delta U over the cycle would be 0. And so you can sum this up. And what we found through our analysis of efficiency, that we have this thing called Q reversible over T, which if you sum over the stages of the cycle, turns out to be 0 too. And in our case, because it's a very discrete and very simple cycle, there's only two contributions to this summation, where you have the isothermal stages of expansion and compression. And by just looking at the expressions, we concluded that this Q reversible over T is the delta of something, much as we saw that delta U, which equals 0, is this summation over the cycle. And what that allowed us to do is define this beast called S, which exactly how the folks who back in the mid to late 1800s arrived at this thing called entropy without knowing anything in deep or too deeply about the particulate nature of matter. So this is how entropy arose, more or less, in a phenomenological way. That we're kind of spoiled now that we have this idea of atoms and molecules, but those people back in that time period had no idea, really a concrete idea of what things and how to define them mathematically and work with them mathematically. So we have S, which is delta S, which is Q reversible over T. So again, I remind you emphatically that this is delta S, not S. Okay, delta S is equal to Q reversible over T between any two state points, which are at equilibrium. And so S is entropy, it's a state function, just like U, age, temperature, volume, pressure, density. And over a cycle, the summation of delta S has to equal 0, much like it would for any of these other functions of state. Okay. And we saw that it's associated, this form of the expression is associated with a reversible process, so that a reversible interaction of heat So the heat that you use in this definition has to be through a reversible interaction between system and surroundings. And then finally, the other immensely important point was that if you have a process that's irreversible, you can still calculate delta S for that process between two equilibrium state points, as long as you can construct, and by imagine, I mean construct a real, a feasible process that connects the two equilibrium state points. And once you do that, you can use delta S as Q reversible over T, or in differential form, ds is equal to dq reversible over T, and you can integrate over that process. Okay, so let me just sort of point out something very pictorially. It's not going to be a very rigorous definition, but in this case, our analysis, and I'm not going to label all of these guys in detail anymore. You've seen it so many times that it doesn't really have to be labeled. So this is our Carnot cycle. Okay. This was just a four-stage cycle for a very specific case, and that is just one engine, if you will. If you had a general process, so let's say you have, and so again, this is a cycle. It's a reversible cycle. But let's say you had any reversible process. Okay, so let's say here's your state one. Okay, and you go through some process on this PV diagram and you come back. So this is some arbitrary thing. It's some general reversible process. Okay, so this is a reversible cycle. And so here we have some general or some arbitrary reversible cycle. Okay, what you can do, and what we can show this mathematically, but I won't, but you can actually construct this cycle as a series of very, very small Carnot cycles. So essentially what you can do, and the drawing, your textbook has a much nicer picture, but you can essentially make these very small differential Carnot cycles and embed them in this cycle. And so I'm going to try, but probably not with. Okay, so there's one little differential Carnot cycle. And that one little differential Carnot cycle would correspond to a ds. Okay. Then you might draw another Carnot cycle. That corresponds to another ds. So these are all very small Carnot cycles that you can use to build up this red general reversible cycle. Okay. That's how this idea or notion of ds comes into play, because now what you can do is just, let's say you wanted to go from state one to, let's say here's state 1A. Okay, so to go from state one to state 1A and compute delta S for 1 to 1A, which is just the entropy at state 1A minus the entropy at state 1, all you would have to do is integrate from state 1 to state 1A ds. Just as if, by analogy, if you wanted delta U to go from 1 to 1A, which is just U at 1A minus U at 1, you would say, all right, well, let's just take the integral from 1 to 1A of du. We can do the same with ds. But for ds, we have this expression now given above, which is the differential form. Okay, so that integral ds from state 1 to state 1A, since this is reversible, is the integral from state 1 to state 1A of dq reversible over T. Okay, and this is how we would get delta S to go from 1 to 1A using this notion of these differential Carnot cycles, these very small differential Carnot cycles that you can use to build up any other cycle. Okay, any questions? Okay, okay. So then what this suggests right? This picture right here, in conjunction with these expressions, this one and this one, right? So these are for the discrete cases, but I just showed you that you can construct another cycle, this red cycle in this PV diagram on the right, in terms of a bunch of little Carnot cycles. And so this summation, this discrete summation over steps of delta S, right, over a cycle, which we set as 0, then becomes, if we have a general process like this just becomes the integral over a cycle. This is our representation of an integral over a cycle of ds, oops, sorry, not dA, ds, which is the integral over a cycle of dq reversible over t is equal to, identically, 0, much as it was here. Okay, so this is a very important result. Okay, so the integral over a reversible cycle right, this holds, and this is and the reason why, well, because S is a state function. Okay, so that's what we have there. All right, so any questions or comments? Okay, so to recap, between any two equilibrium states or state points, and we'll call them 1 and 2, delta S 1 to 2, which is equal to S2 minus S1, is equal to the integral from state 1 to state 2 of dq reversible over t. Okay, so this is a prescription. You might think of this as a prescription. Okay, so maybe you might, or perhaps, you know, some way to think about it. Is like a prescription, or maybe an operational perspective. So it just gives you a set of operations. So to get delta S, you have to do some operations, mechanical operations on your paper or whatever you use. And those operations involve an integral from state 1 to state 2 of this thing called dq reversible over t. Now, it remains for us to define, for any given particular specific example, the form of dq reversible over t. So here's the prescription. It's an operational perspective, if you will. Okay. dq reversible over t must be formulated. That means it must be expanded, or you need to have a little bit more to give you some information about that function that dq reversible over t represents. So that dq reversible must be formulated a little more completely based on the particular specifics of the problem given or encountered. Okay. So you might be thinking, all right, what's dq reversible over t? Well, we'll see that shortly. All right, so I'm going to move on. Any questions, comments? Okay, let's move on then. Now, so far, we have dealt with reversible cycle. Okay, so the Carnot cycle is reversible. Okay, what I'm going to do now is introduce irreversibility to see what the consequences of that are. Okay, so 1, 2, 3, 4. Okay, and we go this direction, this direction, this direction, this direction. So in this case, what we're going to say is that this step we will keep as, oh, sorry. This isothermal step, we're going to say happens irreversibly. Okay, and we are going to just hypothesize that or theorize that. Okay, we just assume that it happens irreversibly. Okay, and we will keep this isothermal step as reversible. Okay, so overall, this cycle is now irreversible. Okay, so the way I've written it, so this process overall is irreversible. So 1 to 2 to 3 to 4 back to 1 is now irreversible. Why? Because we introduce an irreversible step. So that whole thing now is irreversible. Okay, any questions? Okay. All right, so now we're going to analyze this and compare it to the case where we had reversible steps all throughout the cycle. Okay, and so for this, we're going to have to first figure out what the relationship between Q irreversible and Q reversible is, right? And so here's an important side note. Okay, so let's consider a cycle or a process. Okay, we can consider any given process. So let's just say that we go from state 1 to state 2, okay, in some process, okay. So we can apply the first law. And so delta U, to go from 1 to 2, is equal to U2 minus U1, and that's going to equal Q plus W. So this is the integrated form. We're going to look at delta U's, okay? So this is our governing expression, right? So we're going to consider two cases. The first case, we have reversible, which I'll label as REV. And the second case is going to be irreversible, which I'll label as IRREV. And you'll see that in a moment. So in the reversible case, we have delta U reversible to go from 1 to 2, which is going to be U2 minus U1. And that's going to equal Q reversible plus W reversible. If you go from 1 to 2 in a reversible manner. Okay? It's just some abstract way. The other process now, obviously, is going to be irreversible, which I'll label as RRE, whatever, you got it. Okay? So delta U irreversible to go from 1 to 2, which is still U2 minus U1, because at the endpoints, U doesn't matter, right, on the process. So it's still U2 minus U1, the delta U, whether it's irreversible or reversible, okay? But now what we're going to have is Q irreversible plus W irreversible, okay? All right, great. Now what we're going to do, since both of these expressions, this one and this one, give us delta U between states 1 and 2. And we know that delta U between states 1 and 2 is a number. It doesn't matter how you go from 1 to 2. whether it's reversible or irreversible. And so I could label this guy as the reversible, and I could come up with some arbitrary path, which is irreversible, right? So this one is the irreversible if you want. It's just one of many irreversible paths you could have. Okay. Regardless of whether it's blue or red, delta U is going to be delta U. It doesn't matter. So what I can do is equate these two equations, okay, in terms of the Q's and the W's. I can set them equal to equal to one another because the delta U's are the same. Okay. What that leads to is that Q reversible plus W reversible is equal to Q irreversible plus W irreversible. Okay. And now we can do something with the W reversibles versus W irreversibles, because we've seen this already when we considered work. Okay. So what we can do is say, all right, W reversible minus W irreversible is equal to Q irreversible minus Q reversible. All I did there was simple algebra to get all the W's on one side and all the Q's on the other side. Okay, now we're going to analyze this expression, keeping in mind our sign convention. Okay, and our sign convention for W was that when the system does work, W is negative. And when we do work on a system, W is positive. Okay. And we saw that if we do work on a system, which is positive, if we do that work reversibly, it's much less than if we have to do that work irreversibly. So if we compress a gas reversibly, we have to do a lot less work than if we were to compress that gas irreversibly. Okay? And in the case of us doing work on the system, W is positive. So in that case, we see that W reversible is less than W irreversible. Okay, they're both positive. Okay, we'll just use that example because it keeps the sign. It works the same way for the gas doing work, but we'll just keep it as us doing work because everything is easier to visualize. So in this case, both works are positive, but the work reversible is less than the work irreversible. So when we take this difference between W reversible and W irreversible, the SIGN of that side is going to be negative sign. Why? Again, we're going to do work to compress this gas, so the work is positive, the gas being our system. We're going to do work on the system. So both W reversible and W irreversible are positive. However, we saw that reversible process is very special. It's the best we can do, right? If you're going to do work on a system, you want to do the least amount. You don't want to do the most amount, okay? And so that reversible, that very special and unique case gives us an idea of what that least amount is that we would have to do, right? We can be lazy. We can do the least amount of work. And when we take this difference, we get a negative sign. It's less than 0. Okay. That means then, if we go over to the other side of the equal sign where we have all the Q's, since Q irreversible minus Q reversible is equal to W reversible minus W irreversible, and we know that that difference on the left is negative, that implies then that the difference on the right is negative. So the implication here then is that Q irreversible minus Q reversible also is less than 0. And now we have a relationship, therefore Q irreversible is less than Q reversible. Okay, and so we have W reversible is less than W irreversible. We already saw that from earlier. Okay, now we have this new result. But that's not really new because it's just a corollary or a consequence of the fact that delta U is path independent and the relationship between W reversible and W irreversible. So any questions on that? Okay. So if we're going from 1 to 2, okay, in any different set of ways, reversible, and let's say irreversible. Okay. We can take little steps. We can essentially break these two processes right? Break them up into little steps. And I'm using little as a very unsophisticated way, but you get the idea. What I'm doing here is making differential steps, okay? So if I go from 1 to 2, reversibly or irreversibly in differential steps, right? Each one of those differential steps is like saying, all right, well, I have a mini process of 1 to 2. All I'm going to do is add up all those mini processes from 1 to 2, 1 to 2, 1 to 2. So for each one of those mini processes, those differential processes, these same inequalities hold. So what I have then is dW reversible is less than dW irreversible. This is just the same thing, but now all I've done is apply this not to a macro change, but to a very differential small micro change. It's the same thing, right? Because that little differential step is still a delta. It's just going infinitely smaller and smaller to 0 in the limit. And so we have the same thing for dq. Oops, sorry, those things should be with a line. So dq irreversible should be less than dq reversible, okay? And so these are the integrated forms. There's always an integrated form in purple, right? Those are the integrated forms, and then the differential forms are the ones in black at the bottom. Okay, any questions, any comments? Okay, so that was a very important side note. So maybe I shouldn't call it a side note, but it's important. Okay, because now, remember we started asking this question about adding an irreversible step into our Carnot cycle. And because of that very simple addition of an irreversible step, the overall process, unfortunately, becomes irreversible. So the overall process is now irreversible. Okay, so we're going to compare the reversible and irreversible cases of the Carnot cycle. And I really shouldn't say the Carnot, irreversible Carnot, because Carnot is defined by reversibility. So this is some other general, some arbitrary process. This is not a Carnot process because the Carnot is defined as being reversible in all of its stages. Okay. All right, so let's see. We saw that the integral of dq reversible over t for the Carnot cycle, right? So this was the Carnot cycle, it's reversible, was equal to 0. We already saw that in many different ways, in the discrete form and in the integrated form, which I've reiterated right here. So this is the differential form. Excuse me, gotta have my coffee, stay awake. All right, sorry about that. So we have our, so this is the reversible case. Now we can do the same thing over a cycle. Okay, so we're gonna do a cycle, but now we're gonna put in here dq irreversible. My apologies, this probably should go here to be consistent over t. And now we wanna say, well, what is this guy? All right, we may not be able to get an absolute answer like 0 or 1 or something, but let's compare it to the integral, the cyclic integral on the left. Okay, so dq reversible, what we're going to do is, let's see, how should we say this? Let's start. Okay, so let me just ask someone if they can actually see what that integral would be relative to the integral on the left. Does anyone want to take a guess?
Greater than 0.
Greater? Is this Sheldon?
Yes, sorry, less than.
Okay, and can you tell me why you think that?
Because dq irreversible is less than dq reversible, so the coefficient of that, the coefficient will be less than, even in the integrated form.
Right. Good. Right. So that's exactly right. This guy is less than 0. And you can think about it this way. You're right, Sheldon. Very good. Um, if you're going around a cycle, right, and you're comparing just as we did here, right, you can go around that cycle in differential stages, okay, in differential steps, these mini chunks, these mini steps. And if you take mini steps, one being reversible and one being irreversible, what you're going to find as you do that summation, the integral is a summation, right? It's just a summation of these mini things. If you do that integral over the cycle, for every time you do this mini step, dq irreversible, the contribution to that summation of dq irreversible is going to be less than the contribution to the summation from dq reversible, just because of this inequality. Okay, so again, going back to this as our analogy, it's not a cycle, but it gives you the idea of this difference between the reversible Q and the irreversible Q as you sum them over any kind of a process. Okay, so again, the summation, this integral is a summation. Okay, and when you sum the Q reversible, okay, for any given little bit of that path, the contribution from the irreversible path is going to be less than that from the reversible case. Now, if you do this continuously over the whole cycle, okay, we know that the reversible summation, the reversible integral is 0. We already saw that above. But if all of the irreversible contributions are negative as you go through this path, okay, what's going to happen is that they're going to be less than the result for the reversible case. And since the reversible case results in 0, the irreversible case has to be less than 0. Okay? Just because you're adding less each time as you go through that cycle. And that is pure irreversibility. So we can combine these two results, the second of which Sheldon said is correct, the integral of over a cycle, okay? So again, let me just show you that this is PV, it's some irreversible cycle now. 1 back to 1. So this is irreversible. Okay, irreversible cycle. We can combine these two together into one inequality. And that inequality is the integral of dq over t is less than or equal to 0. Okay, and so this is called the Clausius inequality. And this is very important because we're going to make use of it very shortly today. Okay, so this is the Clausius inequality, another very important result, right? And this integral over this cycle of dq over t. So now you see here what this has allowed us to do is now we don't have to specify anything about the q through this inequality. What we have to remember is the two results here, the connections to 0, less than or equal. So the integral of dq over t is equal to 0 when your cycle is reversible, in which case I could have written this as integral of dq reversible over t is equal to 0. And that's what we found through our analysis of the Carnot efficiency. And the integral of dq over t is less than 0 for an irreversible cycle. And again, this could have been integral dq irreversible over t is less than 0. Okay. And all of these, let me just make sure that everyone understands the integrand, right, is this dq over t. So that's why I'm going to put the parentheses like this. And I guess I should put it here just to be clear. Okay. So the integral of this thing dq over t is less than or equal to 0. Okay, so is everyone clear with that nomenclature that I've used? If not, here's another way to think about it. It's the same thing. The integral 1 over t times dq, that's same thing, is less than or equal to 0. This is another way of writing the Clausius inequality, but these two guys are the same thing. Okay, it's the same thing. If you need to see a d something in an integral, that's how one would visualize that. But it's the same thing. Okay. Any questions or comments on that? All right, so now we get to the heart. Now we get to the heart. So here, okay, so the next thing I want to discuss is very profound and very, very important. And so I want to take a breather here just for a few seconds if anyone wants a recap or a clarification or anything like that. Particularly for this, because we're going to use this now. We're going to use this to come to a very profound result that you've seen and been told, but now we're going to see it unfold before our very eyes. I hope, if I do everything correctly. All right. Okay, I don't hear any takers, so I'm going to continue. Okay. So we know that the universe is an isolated system. As far as we know, or at least we assume it's isolated. So let's consider an isolated system first. Okay, so at this point now, we're going to consider an isolated system. Okay, and we'll come back to this connected to the universe. But I wanted everyone to recall that this notion of that the universe is an isolated system. Okay, so recall, according to our current understanding of the physical world and our place in it and our place in the universe, we hold that the universe is isolated. So let's consider a process in an isolated system. So here we have an isolated system, not the universe necessarily yet, but some generic isolated system. Okay. Right. And it's going to be in an equilibrium state 1 initially. And there is an equilibrium state 2. Okay. And through some process, okay, it's going to go from 1 to 2. And that process will be irreversible. Okay. So that process is going to be irreversible. Right? And it's an isolated system. Okay. So this is an isolated system. Okay, so this makes the system isolated. And so what can we say for an isolated system? Delta U isolated is equal to Q isolated plus W isolated. Okay. But what is delta U of an isolated system? Q of this isolated system and W of this isolated system. It's isolated. There's nothing going on between the boundary between that system and the surroundings. Okay. So the system undergoes a process from state 1 to state 2. They're both equilibrium states. Okay. So this system is isolated. So there's no delta U, there's no Q, and there's no W. And keep in mind that this is an irreversible process that the system undergoes. Okay. So for this 1 to 2 process, okay, of this isolated system, Q irreversible is equal to, anyone? For the irreversible process from 1 to 2 of this isolated system, the Q that's associated with it, the Q irreversible in this case, would be, what value would it have? No one wants to take a guess? Zero. And that's because that's equal to this, right? Because you have this isolated system, and for an isolated system, there's no interaction with the surroundings. Q has to be zero. So during this process, which is irreversible, Q irreversible is equal to zero. Okay? Any questions or any is that confusing or is that clear? Okay. So we can say that this is to go from 1 to 2 for the system. Now what we're going to do is to create a cycle. And what we're going to do for this cycle, now we will go from 2 to 1. We will go to from 2 to 1, equilibrium state 2 to 1, but we will do this in a reversible manner. In a reversible manner. Okay, so somehow now the system is no longer isolated. Okay, the system is no longer isolated. Okay, so in that case, there's going to be some heat interaction. Okay, so we're going to go back from 2 to 1, and I'm going to make that process look like this. Okay, and I'm making it red to indicate that it's no longer an isolated system. And I'm going to dash it. Okay, so this red process is reversible. Okay, and the system is no longer isolated. Okay, and that's okay, right? Everyone gets it, because if it's not isolated, then it can have a heat interaction. Okay, so that's what we're going to do. We're going to bring it back to this reversible process, okay, in which there is a heat interaction. So when we go from 2 to 1, there's going to be a Q reversible to go from 2 to 1. Okay, everyone following, or is there some issues that I need to address at the moment? Okay, so if we go from 1 to 2 and then back to 2 to 1, with 1 to 2 being irreversible and 2 to 1 being reversible, we have a cycle. And what is the nature of that cycle in terms of reversibility? Is it irreversible or reversible? The cycle.
Irreversible.
It's irreversible. That's exactly right. This is an irreversible cycle, right? Because why? Just as we did with that Carnot example above, we added an irreversible stage. Okay. So even though we have one reversible stage, that single irreversible stage makes the whole cycle irreversible. Okay. So what we can do now is apply the Clausius inequality for this cycle. Okay. So the integral over the cycle, we go from 1 to 2 back to 1, of dq over t, okay, is going to equal the integral from 1 to 2 of dq irreversible over t plus the integral from 2 to 1 of dq reversible over t. And remember, since that whole cycle is irreversible, this all is going to be what in terms of its relation to 0? Because the whole cycle was irreversible, this will be
less than or equal to 0.
okay. Since this is irreversible, the Clausius inequality tells us that it has to be less than 0. Okay, so it tells us it has to be less than 0. All right. So the irreversible step happened with an isolated system. And we saw that for that case, Q irreversible is 0 to go from 1 to 2. So in that case, dq for the process from 1 to 2 has to be identically equal to the value of 0. Does anyone not see that? Okay. Okay, great. So because the system was isolated here for that first stage, there was no heat interaction, so that has to be 0. But this guy is not 0. So we're left with this term. Let's kind of bring this down. Okay, so let's kind of bring this down. And what we have here is the integral from 2 to 1, the reverse of dq reversible over t is less than 0. But what is our definition dq reversible over t? What is that defined as?
Delta S.
We have to be careful.
DS.
ds. And for what state, what process? This is ds going from 2 to 1. Remember, so that has to be consistent with our integral, the limits of the integration. Okay, does that make sense to everyone? So in fact, what we have is ds to go from 2 to 1 is less than 0. But what is the integral of ds if we go from 2 to 1? Now, whoever said that first answer can say it again. That's going to be, the integral is going to be
Delta S.
And that subscript will be 2 to 1 is less than 0. Now, the original process that we were considering was this irreversible process in an isolated system. That 1 to 2, the black process, that was irreversible. So if we wanted to say something about delta S for that irreversible process, right? What happens if I want to go, and so this delta S is going to be S1 minus S2, right? Because we're going from 2 to 1. The final state here is 1. So this is going to be S1 minus S2 is less than 0, right? But if we are going through that original process where we're going from 1 to 2, this S1 minus S2 becomes I just flipped the subscripts, right? So this becomes S2 minus S1. But what happens to the inequality sign?
It flips as well.
Yeah, it becomes this. And what is S2 minus S1? That's just and so what we found using our Clausius inequality and this notion of the relationship between reversible and irreversible heat is that the delta S for this irreversible process in an isolated system, remember, just going from 1 to 2, the system was isolated. That was how we constructed the experiment or the process. So in that isolated system where we really didn't have anything known about it, as the system went from state 1 to state 2 irreversibly, what we found is that delta S increased, is greater than 0. And so this was for the isolated system. Okay, and so what we have is a conclusion now, a very profound conclusion, that delta S is greater than 0 for irreversible processes in isolated. And so this is a mouthful, and each one of these words, including that inequality, is very, very important. And this is one of the most profound results that we can see, we've actually seen unfold before our eyes. Okay, that delta S for an irreversible process in an isolated system. All of these words are very, very important. So if you want to say delta S is greater than 0, you have to use these words. Okay, at least at this point, the way we've come to this result here. Okay, just bear with me, I'm done almost. So what this is saying is that if you want to go back to our notion of the universe, which is an isolated system, the universe is an isolated system. For any irreversible process that occurs in the universe, there has to be an associated increase in the entropy of the universe. So I know you've been told that entropy is associated with this thing, that the entropy of the universe increases, etc., etc. It is much more specific and much more nuanced than just that statement. The sophisticated, the nuanced, and the true statement, as far as we understand it based on our knowledge of math and physics today, is that the entropy of an isolated system increases when there is an irreversible process occurring in that isolated system. Okay, so all of those words are very, very important to keep together when we talk about entropy increase. We will talk about entropy increases in other scenarios, but for the moment, if you want to relate delta S increase or entropy increase with the universe, it has to be said in this way, because this is the way that it is. Okay, so the entropy of an isolated system, for example, universe, increases when you have an irreversible process taking place in that system. Okay, I'm going to stop there. And I'm going to let you ponder this very profound result. And we will continue with applying now what we've learned to actual problems next lecture. Okay, and for the remaining moments, I will open this up for questions if people have any questions. So this is very important. Okay. And so this is upper level. This is why this is an upper level course. Okay, I don't hear any people asking questions or wanting questions. So I'm going to end the lecture at this point, and I will upload it, and I wish everyone a happy rest of the week, and I will see you Friday. Thank you everyone for your attention.